taint-based call graph construction for Java objects deserialization, presented by Joanna Santos.
All right, so good afternoon, everyone. Sorry for some minor technical difficulties in here. It is my pleasure today to present our work on call graph constructions for object deserialization. So to start with, call graphs are data structures that are very important for several interprocedural client analyses. And that means that if you have a call graph that is unsound, your client analysis will all be unsound as well. So one of the key challenges that we have when we are building call graphs, at least static analysis, is that certain dynamic programming features will make it challenging for us to infer what is the possible dispatch at a given call site. And in fact, there was a previous work that was published at OOPSLA in 2019 that investigated the soundness of different call graph algorithms with respect to certain programming features. One of these programming features was object deserialization. And as you can see here in the table that they reported in the paper, the deserialization was really not well supported by the existing techniques. So motivated by this fact, what we want to do is we want to build the call graphs that are sound with respect to this feature. But before I talk about my technique, let me take a step back and explain what exactly is object deserialization. So object deserialization is basically the process of you have an object in your memory, and you want to save this object. Somehow, you have to convert this object that is in your memory into some sort of format. Could be a stream of bytes, could be JSON, could be XML. So this process is called serialization. Now, once you save that object and you want to actually use that object in your program, you have to convert it back from that stream of bytes back to the object in the memory. And that process of converting from this representation of an object back to an object in the memory is called deserialization. And object deserialization, serialization is available in multiple languages, such as Python, Ruby, PHP, Java. In fact, if you implement a machine learning algorithm, more likely you're saving your object, saving your model in a file. So that's exactly object serialization right there. So when it comes to Java, and not only Java, but several object serialization libraries, what we have is that developers, they are able to customize the process of serializing these objects. So for example, let's take a look of Java. When you're writing an object in Java, you're going to use the class called object output stream. When you use this class, what happens behind the hood is that, well, the object that you're saving at that stream of bytes, it's going to be serializable. So it has to implement the serializable interface. And if that object implements, the class of that object implement these callback methods right here called write object and write replace, these methods are invoked when that object is being saved. Similarly, when you are reading that object back from that stream of bytes back to the code, back to your program, if the data type of that object also implements certain callback methods, such as read replace, read object, these callback methods right here, they're also invoked during the deserialization process. So what happens is that existing call graph construction algorithms, they do not take into account these callback methods that arise at runtime, and because of that, these call graphs become unsound. So our goal in here is exactly to build a technique that can plug into existing call graph construction algorithms and can find these hidden methods, okay? These hidden edges. So how does our approach work? It works as follows. So this is a two-phase approach that relies on the tainted states of objects to be able to compute a method dispatch. So how does it work specifically? So the first thing that we do is that we build an initial call graph that is supposed to be refined later. So at this initial phase, what we do is that we first take some things that is input, which is the program itself, a list of entry point methods, and what pointer analysis method you want to use, okay? So after we do this initial analysis is that we start from the entry point methods, and what we do is that we identify what places in our program are reading or saving objects, okay? So at these call sites, when we do, hey, read an object or save an object at this file, what we do is that we replace these invocations to syntactic methods. So the idea of the syntactic method is really to act as a placeholder of instructions to basically model how the serialization process will look like at runtime. So what we do is that at these serialization points and deserialization points, we created these synthetic methods. Now, at this initial call graph construction phase, these synthetic methods, they are empty. So they don't have instructions yet, but they need instructions, right? So what happens is that on the next phase, what we do is that we actually refine this call graph, these synthetic methods, to include instructions. So just as an example in here to clarify what is going to happen on this first phase, here at my left, I have an example of a Java code that is saving a list of students, an array of students, in a file. So as you can see here, when we build this initial call graph, we have a call graph that starts from the main method and has a few edges to the constructor of the classes being serialized. So for example, today's student class and today's TA class as well. But as you can see here at the last call site, at line 11, when we do out.writeObject, noticing here that what I have is a node in my call graph, and that node is synthetic. That's why I'm highlighting that in yellow, okay? So what I'm going to do now on the next phase is get these synthetic methods in here and refine them, and add instructions to model how the deserialization process will look like. So now what I want to do next is, well, let's go ahead and refine these methods. So that's exactly the purpose of our second phase right here. So what we do is that we get this initial call graph, and we start expanding it. So how do we do this refinement? So the refinement happens through something called API modeling, which basically what we want to do in here is that let's try to model the behavior of the serialization API. So when we are modeling the serialization API, so that means when we are modeling the behavior of the program when it comes to saving objects, essentially what we do is that, well, we look at the type of that object. So we look at the points to sets of that object to be able to infer what is the object being saved. And what we do is that inside of our synthetic method called writeObject, what we do is that first we say, hey, we're going to downcast that object, we pass the subparameter in here to that data type. And then finally, we're going to invoke the callback methods in here, okay? So noticing here that if this object in here, the data type of that object, implements those custom callback methods, they are going to be invoked by our synthetic method. Similarly, an object can contain other objects in the fields. So if those fields are also serializable and they also implement callback methods, those callback methods are also invoked as well. So as you can see here on the next line, what we do is that we read the values of these attributes, and then we downcast them, and then we invoke any callbacks that they may have, okay? So this process happens for all fields for that object. Now, that was to model writing an object. But how about reading an object? When it comes to reading an object, that process is slightly more complicated. And the reason is quite simple. When you read an object in Java, that object can be of any type. As long as you have classes in your program that implements the serialized interface, any of those classes, their instances can be read right here, okay? So at a given read object call site, any of those data types can be read back. So we have to be a little bit smarter when we are trying to model this behavior right here. So basically what we do is that, look, when you're reading an object in your program, we soundly assume that any classes that you have, any objects, will be any serializable class in your class path, including your application classes, library code, any of those data types are possible to be read right here, okay? And we also make a few assumptions. One assumption is that we don't assume that you're going to do dynamic loading. So only the classes that we observe at the class path are only the possible data types to be read. Another thing that we assume as well is that all of the fields in our objects are not null, so that we can infer that there are possible callbacks for these fields. And also, we look at the taint states of objects to be able to compute the method dispatch. All right? So let's take a closer look on how this algorithm looks like. So as I mentioned before, the taint states of objects will dictate how methods are going to be computed, how the dispatch will be computed. So if we are talking about taint analysis, the first thing we have to talk about is some common terminology here, which is, so now every method in my program will have a context, and each variable has an associated pointer. And that pointer is basically for a variable under a given context. And each pointer now has also a taint state. And that taint state indicates whether that pointer is tainted or not. So now, what we want to do in here is that, well, let's look at those tainted states when we are computing the method dispatch. So first thing we have to do is that we have to implement this taint. We have to start flagging some objects in the program. So in this case in here, the way we flagged these objects as tainted is that basically any object that implements a callback method is tainted. So initialize those objects as tainted. So noticing here that on my syntactic method, I'm creating an object of type cache manager. That object will be flagged as tainted. Now, what we also do is that all of the fields of that object will also be initialized as tainted as well. Because if the object itself is tainted, all of its attributes are tainted as well. So this is how we initialize the taint states. Now, the other thing we have to do as well is that if the object is tainted, that means this pointer has also to be flagged as tainted. Okay? Now, the next thing that we have to do is we have to propagate states to variables in the program. And that propagation follows the semantics of Java. So when you have an assignment, that means that if the right-hand side pointer is tainted, that means that the left one should also be tainted. So essentially what we do is that we propagate the taint state from the right side to the left side. One thing I'd like to highlight in here is that the taint states are never removed. Okay? Now, when it comes to method calls, now we have going to take into account these taint states when we are computing the dispatch for these possible method calls. Okay? Now, the first thing that we have to do as well is we have to propagate the taint for those method calls. So essentially what we do is that we propagate the taint from the arguments to the parameters of the invoked methods. And then the other thing is that if that method is returning a value, the taint state of that return value should propagate to the value. Another thing that we do as well, which is in the case of instance methods, what we do is that we propagate this pointer as well. So if the receiver object is tainted, this pointer at the caller should also be flagged as tainted. So once we do that, now we can take into account those taint states when we are computing the dispatch for a given method call. So noticing here that at this example, I have x equals to an object O, and I'm invoking the method G and passing some arguments to it. So when I compute the dispatch, what I do is I take into account what is the data type of O, the static type of O, the context in which that object is, and the method signature. And what I do is that basically I look at what are all the possible serializable classes in my class path, then what are the classes that are actually accessible at that given context, because remember in Java some classes can be public, private protected, or package protected, so we also take that into account. And another thing that we also take into account, whether that class is type safe to the static type of O. So that means we compute the intersection of these three types in here, and the possible dispatch will be all the methods that match the signature of G that are from these classes in here, that is in that set. So once you do that, once we compute the dispatch, we add these methods back to the work list of methods because our algorithm to build call graphs is iterative. So it keeps analyzing these methods until there are no more methods to be analyzed on our work list. All right, so with that, we now evaluated whether our approach is actually sound or not. So we answer that by looking at two data sets. One is a data set of test cases by our previous work, and then another one is a data set derived from the. And here what we look is that we look at how many test cases we passed and how many edges are in our static call graph that are not in the runtime call graph. So once we look at the soundness results, we can see that Seneca actually passed all the test cases for the first data set. And when we look at the performance of Seneca on the second data set, which is a data set of real Java programs, we can see that our approach actually overperformed the state-of-the-art. You can see here that our call graphs are more sound than the state-of-the-art approaches. Now, another thing we have to look at is the precision. Is our call graph decreasing the precision of the call graph? So what we look in here now is a different metric, which is how many nodes and edges are in the static call graph, but not in runtime. So when we look at this, we can see that actually our approach also overperforms a state-of-the-art approach. And this is also, we can also observe that when we look at the X corpus data set. And finally, another thing we looked as well is whether, now that we have this sound call graph, would this call graph be useful in a client analysis that is being used for vulnerability detection? So what we have done in here is that we built a client analysis that tries to find vulnerabilities caused by untrusted object deserialization. And what we have done is that we got 3 open source projects that have known deserialization vulnerabilities in them, and then we used our call graphs to see if we can find these vulnerable passes or not in the program. So as you can see here, when we compared our approach to a state-of-the-art approach called SALSA, we can see that our approach was able to find vulnerable passes in the program, including the vulnerable pass that was the one that had the actual vulnerability. But the state-of-the-art approach was not able to get any vulnerable pass. Okay? So with that said, just to wrap up, we built an approach to improve the soundness of call graphs with respect to object deserialization. And compared to the state-of-the-art approach, our approach improves the call graph soundness without greatly decreasing the precision of these call graphs. And as you can see on the previous slide, this call graph was useful for a client analysis for vulnerability detection. With that said, I'm happy to take any questions that you may have. Thank you.
Any questions? Can you say something about how difficult is it to incorporate this approach in an existing call graph constructor like Duke or VALA or any of the others?
Excellent question. So this whole approach in here was actually built on top of VALA. So what we do is that, well, you select what is the pointer analysis algorithm you want, if you want 0, 1 CFA, N CFA. And then what we do is that we build this on top of it. So we modify the points to sets, and the taint states is also built on that. So it's not straightforward, but it was already built on top of VALA. So all the data structures that we are using is on top of VALA. So if you build an algorithm on top of VALA, our approach will work as well. So it would integrate just fine.
And is it something that is easily localized in a single component, or is it that you have to make changes all over the place to incorporate this technique?
We did not have to make any changes at the VALA side, so it's really localized.
Okay.
Yeah, it's modular.
Please step up to the microphone.
So I enjoy your talk, and I have one question that I'm curious about. So you mentioned modeling the behavior of the serialization API. You talked about the cases for reading and writing an object. Mm-hmm. And I'm wondering whether, because all of these are approximations of actual runtime behavior, I'm wondering whether, you have an idea of any failure modes that you've encountered following such a model?
So are you asking about limitations of the modeling part?
Yes, or any directions for future work that you have in mind.
Excellent question. So some of the key challenges in here it comes with collections. So the way we assumed is that when you have a collection, we just assume that we look at the static type of the collection, and then we assume that, well, that collection can have at least one. That means that there are several edges in there that will not arise at runtime. It is possible not arise at runtime likely, right? So it makes it more imprecise, but it sounds can arise at runtime. There could be a program that has those edges. So a possible future that we could tone this down a little bit so that it's not as imprecise. Yeah.
I see. Thank you.
Yeah. Thank you.